Well, good evening and welcome to this webinar presented by the IET's Anglian Coastal Local Network, which represents members in Norfolk and Suffolk, and welcome also to folks from other parts of the UK and indeed globally. I'm delighted to welcome you all. I'm Kevin Foster and I'm chairman of the Anglian Coastal IET Local Network, and I'll be your host for this evening. We will leave questions until the end of the presentation. So without further ado, I'm delighted to introduce our speaker, Thanos Gekelias. Thanos received his MEng in Electrical and Computer Engineering from the Aristotle University in 2000. He received his MSc and PhD degrees in 2001 and 2006, respectively, from King's College London. Currently, he is a research fellow at Imperial College London. Now, in 2008, he was at Bell Labs Research Centre, Alcatel-Lucent in the UK, working as a visiting researcher on wireless mesh networks. And from 2009 to 2013, he served as project manager for the University Defence Research Centre in signal processing at Imperial College, sponsored by the MOD. Now, over the last 20 years, he's been involved and made significant research contributions to several and diverse ICT projects funded by the European Commission, EPSRC, UK MOD, and the United States Army. His scientific and technical expertise lies in the area of wireless communications, signal processing, networks, localization, machine learning, algorithmic design, modeling, and optimization. So Thanos, over to you.
Thank you, Kevin. Before I start this talk, let me also add a couple of lines related to my involvement in localization-related research and technology. My first involvement was in 2000 during my master research thesis, where I implemented localization techniques for a 3G network simulator. Later on at Imperial College, I was involved in WINE CPSRC project, where we were tracking relative movements of sensors in tunnels to detect any structural movements. Then a few years ago, through another EPSRC project at Imperial, we developed a Wi-Fi based localization system to detect people movements in public places. The system was based on receiving signal strength fingerprinting techniques that I will describe later on. And we had a successful field trial in one of the major UK airports to calculate queuing delays during check-in. And finally, recently, I also worked as a principal researcher at project management in a research project sponsored by Ministry of Defense, trying to detect and locate underwater objects using electromagnetic signals. So different environments, different techniques, different technologies, and different objects to be located and tracked. And, let me share now my screen. And let's start this presentation. Okay. So the outline of this presentation, I will start with a brief description of what is indoor localization. Then I will describe different localization techniques, some performance evaluation metrics and trade-offs, some indoor localization technology enablers, technologies that allow us nowadays to detect things in indoor environment. Then I will give a prime on Internet of Things, and I will finish with some IoT and indoor localization challenges. So, localization is the process of obtaining a user or device location in space as an absolute position, for instance, finding the longitude or latitude, or with respect to some reference points. So this is not something new. In the 13th century, sailors were using the mariners' astrolabes, an inclinometer used to determine the latitude of a ship at the sea by measuring the sun's noon altitude, or the meridian altitude of a star of known declination. Then the 70th centuries, people were using another device called sextant, a navigation instrument that measures distance between two visible objects. The primary use was of a sextant was to measure the angle between an astronomical object at the horizon for the purpose of celestial navigation. Then much later, since early 1980s, we are using satellites as reference points and what is known as Global Positioning System, or GPS for short, as reference points to find our absolute locations and navigate on the Earth with up to a few meters accuracy. And later on again in late 90s, early 2000, where the cellular technology matured enough, we had the first 3G network deployments, and with that we had the first very primitive indoor localization services. And we come to our days now with all these local area network smartphones and other sensors and devices that we can provide indoor localizations with very high accuracy indoors. So indoor device localization has been extensively investigated over the last few decades, mainly in industrial settings and for wireless sensor networks and robotics. However, it was only less than a decade ago since the wide-scale proliferation of smartphones and wearable devices with wireless communication capabilities have made the localization and tracking of such devices synonym to the localization and tracking of the corresponding users, and enabled a wide range of related applications and services. This kind of applications include the health sector, industry, disaster management, building management, surveillance, asset management, and many other and various applications. So before we start the description of different localization techniques, let me define 3 different types of localizations that, although they look very similar, each of them has different requirements in terms of energy efficiency, scalability, and performance. So what we have is the device-based localization, which is the process in which the user device uses some reference nodes or anchor nodes to obtain its own relative location. It is similar to the GPS process and mainly used for navigation, where the user needs assistance in navigating around any indoor or outdoor space. Then we have the network-based localization, which is the process where a set of anchors or reference nodes passively obtain the position of a user or an entity connected to these reference nodes. This is actually the inverse process to device-based localization. This is mainly used for tracking the users or assets and then accordingly provide different services. And finally, you have the proximity detection, which is the process of estimating the distance between a user and a point of interest. And the proximity detection has recently been seen as a reliable and cost-effective solution for context-aware services. So before I go to the localization techniques, as I said earlier, the reason why we are able now to detect things indoors is mainly because of the advances we have in the radio propagation, radio-related and network-related devices. So it would be nice if we first understand what exactly we mean by radio propagation, signal propagation, because this is what we're going to use to describe most of the techniques and see how it works. They work later on. So first of all, amplitude of phase. Every signal propagates as a wave. So as you can see here, it has an amplitude and a certain phase. And this is something that we can detect. We can have that information. We can use it for localization. Then we have the signal power attenuation, which is also called path loss. So essentially, the radio signal attenuates exponentially as it propagates through the air. And as many of you are engineers, you know that this kind of loss usually expressed in dBs. There are many, many different forms, more or less complicated, to calculate this path loss. One of the most common and most simple one is this one, where L, the path loss in decibel, is equal to 10 times N, where N is the path loss exponent, a number that depends on the environment. It can range from 2 in free space to 5 in indoor environments, times the logarithm of D, which is the distance between the transmitter and the receiver, and C, which is a constant that accounts for system losses, or is the signal in a known location. So we use C as a reference point. And this signal attenuation can be used again for signal detection and localization. Then we have the propagation time. So the velocity of the radio waves is approximately equal to the speed of light, which is 3 times the 8th power of 10 meters per second. So for example, in 10 nanoseconds, a radio signal in the frequencies that we use can propagate up to 3 meters. Another very important assumptions that we made is that is the plane wave propagation. So although it propagates in a spherical way, when it is far away from the transmitter, and this is few wavelengths away, it can be approximated by a plane. And this simplify a lot the mathematics we are using it enable us to use many different localization techniques and signal processing. Then we have the multipath, which is actually the biggest problem in indoor localization. So the radio signal reflects on walls and other objects, as we can see here, on the walls, on doors, other objects. And then what you receive is usually the direct wave, if you're lucky enough to have one, and then you have multipaths from other directions. And all of these signal vectors combine and distort the direct signal, and can be approximated by different distributions such that expressed the shadowing and Rayleigh fading. And here you can see the indoor power delay profile, which is shows the signal, how the signal will look like the very first nanoseconds of the reception. And as you can see, it's very difficult to distinguish between the direct transmission and the multipaths. And finally, we have the propagation through objects and walls. So the attenuation depends on the object material and also the frequency. With higher frequencies, attenuate more than the lower ones. Okay, now, and this is actually a nice graph that you can see how the signal is affected. So with a straight solid line, you have the path loss, the attenuation in dB of your signal as a function of the distance. Then with the dotted line, you have the shadowing fading, which is, it doesn't happen very frequently. And then you have the Rayleigh fading, which is a very, very, very rapid changes of your signal over time and space. So this is what we get, so you can understand from how difficult it is to detect things. So let's go now to some of the localization techniques that we are using. The most popular technique is the received signal strength, or RSS, which is exploits, as the name says, the signal attenuation or path loss. So the RSS is the actual signal power strength received at the receiver. It usually is measured in decibel, milliwatts, or just in milliwatts. The absolute distance can be estimated using different signal propagation models, like the one we described earlier. And what you may have seen, and if you have been experimenting with this kind of localization techniques, is what many devices provided. This is the RSSI. RSSI, which is often confused with RSS, is the RSS indicator, is a relative measurement of the RSS that has arbitrary units and is mostly defined by chip vendors. So different devices, they will give you a different kind of measurements. Usually they scale from 0 to 80, 0 to 100. So using that RSSI values and the symbol path loss model, like the one we described before, we can calculate the distance between the transmitter and the receiver. Now, when we know that distance, and we use that distance from multiple points, we can use triliteration or endpoints literation. And as we can see here, the intersection of these circles that represents the calculated distance can give us the location of the device that we want to track. The main advantages of this technique is it is simple, it is cost efficient, it can be used on existing wireless technologies without main modifications. The main disadvantages is it may have poor localization accuracy in non-line of sight conditions due to reflections from the walls at big objects. And also, you will have also lots of severe fluctuations due to multipath fadings and indoor noise. A way to improve that is a technique called fingerprinting. Fingerprinting is a technique that is using a survey, initial survey by engineers in the environment that we want to track. So it contains two phases: the offline training phase, where we record the signal strength, RSSI, from several transmitter access points in range. And then we store this information in the database together with the known coordinates of the tracking devices. So we move with a phone or another device. We transmit signals and we write down the coordinates of the location of transmission. And this goes in our database. Then in the online tracking phase, we have the current RSSI vector at an unknown location. So we have the received signal now, and we compare this to those stored in the fingerprinting database and find the closest match, which is represents the estimated user location. And there are different techniques to do that, as k-mean, k-nearest neighborhood, maximum likelihood, etc. So the main advantages of these techniques, it requires no signal propagation models. It is immune to non-line of sight and multipath propagations. The main disadvantages, though, is that it requires a costly site survey to build the radio map. It is susceptible to changes in the environment, and mobile sensor antenna directionality, it may distort the accuracy. So when you move with your phone in your pocket, your phone does not transmit in an omnidirectional way. So this angle of transmission, the beams of transmission, will affect that RSSI values that you receive, and when you compare it with the offline data. The next technique that is very popular is the angle of arrival or direction of arrival, which is using multiple antennas to estimate the angle at which the transmitted signal impinges on the receiver. So as you can see here in the graph, the phase shift differences at the receiver signal arriving at the antennas is used to compute the angle of arrival of the signal. And there are several multi-resolution techniques since 80s, like music or Esprit, that help us to find this with very, very high accuracy. After we have that information, we can apply triangulation, which is very similar to triliteration. Instead of trying to find the intersection of the circles, we have to find the closest intersection of lines to locate our device. So the main advantages is that this technique can be very accurate when transmitters and receivers are in a close distance. And also it may be possible to do that by using only 2 monitors in a 2-dimensional space or 3 monitors in a 3-dimensional environment when we avoid the front bank ambiguity in the antennas. The main disadvantages is that it may require more complex hardware and multiple antenna receivers. It requires careful calibration and precise orientation of the antennas, because a slightly movement of the antenna can change, the receiver can change the estimated angle. The accuracy deteriorates with the distance, as you can expect. A small angle will give you a small distance error when you are close to the receiver, but the further away you go, this distance becomes bigger and bigger. And obviously, it requires the line of sight. Otherwise, what you will detect is the reflection of a multipath. Then another popular technique is the time of arrival or time of flight. This exploits the signal propagation time to calculate the distance between the transmitter and the receiver. As we said, the signal propagates with the speed of light, and this can be used to calculate the distance. The time of arrival requires strict synchronization between transmitters and receivers, and in many cases, we may use timestamps as well in the packets that we transmit to get that information. The key factors that affect the time of arrival estimation accuracy are the signal bandwidth and the sampling rate. The signal bandwidth is related to how accurate we can detect the direct multipath direct signal from any other kind of multipaths. We want to have the time of arrival of the direct signal. Otherwise, what we will calculate is not the direct path, but the reflection through objects. So the main advantages is that it can be very accurate in line of sight transmissions, and you have high synchronizations. But this is also one of the disadvantages, because this requires hardware clock synchronization. When you have multipaths and narrowband transmissions and non-line of sight, this technique will fail. So we have now a couple of techniques that are very similar to that, which is the time difference of arrival, which exploits the difference in signals propagation times from different transmissions. This is different from the time of arrival, where the absolute signal propagation time is used. So now what we have is, instead of circles, we have hyperboloids, and we need the intersections of 3 hyperboloids from different receivers in order to calculate the exact location of the transmitter. We have hyperboloids because we don't, not circles, because what you calculate is the difference between these 2 circles. So strict synchronization is required, but in this case, it's synchronizations between only the transmitters. It's not between the transmitter and the receiver. Another technique that is related to time of arrival is return time of flight, which measures the round trip. This is from transmitter to receiver back to the transmitter of the signal propagation time to estimate the distance between the transmitter and the receiver. The return time of flight estimation accuracy is affected by the same factor as time of arrival, but it can be more severe, because what you have now is the signal is transmitted at the receiver twice, so the error of the estimation can be double. We have a couple of additional problems. Is the response delay at the receiver, which is highly depends on the receiver electronics and protocol overheads. This is the time that takes for the receiver to receive the signal and report it back to the original transmitter. And this delay can be ignored when you have in outdoor localization schemes, but where you are indoors and the distances are small, this can give you a big error. And before we move to the technology enablers, let's see what are the main performance and valuation metrics and trade-offs between these techniques that will help us then to understand better why we use that localization technologies. So first of all is the localization accuracy. This is probably the most important metric, and this is the question that everybody will ask you about if you develop a model. And the answer that you will receive if you ask someone is probably misleading because it depends on many and various parameters, which is the environment, the technology, the definition of this, or the definition of the localization. So it depends, for example, of how far away you are from the transmitter or the receiver. Within the same environment, if you are close to a wall or in the middle of the room, you will have different localization accuracy. If you read an academic paper, you will find out that the accuracy is much more precise than if you read a manual from an industrial business that provide indoor localizations. What value you should expect for indoor environments is from few centimeters to several meters. And there are several trade-offs between localization accuracy and everything else. Whatever you change in your system will affect the localization accuracy. So the other thing is the cost. So the questions you have to ask is, can existing network infrastructure can be used? We are using radio signals, so can we use any of the existing infrastructure we have, like the Wi-Fi of our office to do the localization, or we have to build something from scratch? Is the underlying technology proprietary or free open source? Can I use some hardware from the shop, or do I have to develop things myself? How expensive are these sensors, particularly if you have to deploy many of them? Is the cost of the data processing, does it require a very extensive data processing in local servers or in the cloud, etc.? And obviously the cost, what devices you are going to use, what sensors you are going to use, what electronics, it will affect your localization accuracy. Then we have the energy efficiency. If we use dedicated sensors, the question is how long do the sensors battery is going to last? If you don't use dedicated sensors and you try to locate a mobile phone that you run other applications, is what will be the additional energy consumption of the localization techniques? Then is the network infrastructure, the sensors that you put on your walls. Are they battery based or they are connected to electricity plugs? Are there any energy consumption for communication? We collect data, all this data, we have to somehow to transmit them and to process them. And this comes to the next bullet point, which is the energy consumption for data processing. So there are lots of trade-offs here. The energy consumption related data collection and transmission frequency is how often you may transmit a beacon signal in order to do localization, will affect your energy consumption. At the same time, will affect the localization accuracy, because the more of the signals you have, you will do better averaging, better filtering, you can have better accuracy. This is also related to the latency. How often do you transmit? If you transmit every few seconds or if you transmit every milliseconds, this will affect the latency of your localization. Then is the transmission and reception rates, which will first of all affect the network planning. It can reduce the number of installed devices at cost, which is also the hardware and maintenance. The dense network deployment is not preferable in many environments. If you go, for example, to a hospital or an airport, they will not allow you to put your sensors wherever you want and as densely as you would like in order to provide a very accurate service. So as you can see, the trade-offs between the transmission rates, the energy efficiency, and the localization accuracy exist. Then the latency, as we say, can I have a real-time localization prediction or not? Obviously, this latency depends on the application needs. And as I described earlier, multiple samples are needed to remove noise and improve accuracy. The next thing is scalability. So how many devices can I track at the same time? We're talking later for IoT. IoT have 1,000 devices probably within the same building. Can your localization technique scale? What will be will the cost increase with the number of devices and the area of coverage? So there are trade-offs between the scalability, the cost, and also the latency of the system. And finally is the availability. Can I use existing network infrastructure, and what is the technology penetration rate? Is it something that is used already by most of the people, or is something that nobody has it before? Can I buy it off the shelf, or is purpose-made? And is the underlying technology proprietary or free and open source? So having all this back in our mind, let's see now what are the technology enablers that allow us up to that point to do indoor localization. And first of all is the Wi-Fi or 802.11, a protocol that most of you are familiar. This standard is commonly known as Wi-Fi, operates in the industrial, scientific, and medical ISM bands, which are around 2.4 and 5 gigahertz. It is primarily used to provide networking capabilities and connections to the internet for different services in private, public, and commercial environments. Initially, the Wi-Fi had a reception range of about 100 meters, which has not been increased, which has now been increased to about 1 kilometer in the 802.11a8 standard. Most of the current smartphones, laptops, and other portable devices are using Wi-Fi. That's why it's an ideal candidate for indoor localization. And this is one of the most widely studied localization technologies in the literature. So since existing Wi-Fi points can be also used as reference points for signal collection, basic localization system can be built without the need of any additional infrastructure. However, since these Wi-Fi networks are normally deployed for other purposes, which is communication and to maximize data throughput and network coverage rather than localization, they will not operate that well. Therefore, novel and efficient algorithms are required to improve the localization accuracy. Moreover, the uncontrolled interference in the ISM band, where everybody can transmit without a license, has been shown the effect that affects the localization accuracy. Next technology is Bluetooth, or the IEEE 802.15.1. Bluetooth consists of the physical and MAC layer specifications for connecting different fixed or moving wireless devices within a certain personal space. The latest version of Bluetooth, which is called Bluetooth Low Energy or BLE, also known as Bluetooth Smart, can provide an improved data rate of, I think, 24 megahertz. The coverage rates up to 70 to 100 meters, with higher energy efficiency as compared to the older versions. And while BLE can be used with different localization techniques such as RSSI, angle of arrivals, and time of flight, most of the existing BLE-based localization solutions rely on RSS-based inputs since they're less complex. So even though BLE in its original form can be used for localization due to its range, low cost and energy consumption, two BLE based protocols have been proposed recently. The one is the iBeacons by Apple and the other is the Eddistones by Google. Both of them mainly aim to provide context-aware proximity-based services. So they don't. These are beacons. These are protocols that what they provide is purely localization and no communication or other kind of functionalities. And finally, we have ultra wideband, which is ultra short pulses with a time period of less than 1 nanosecond, transmitted over a large bandwidth, sometimes over than 500 megahertz, in a frequency range from 3.1 to 10.6 gigahertz. They're using a very low duty cycle, which results in reduced energy consumption. The technology has been primarily used for short-range communication systems, such as PC peripherals and other indoor applications. Ultra-wideband has been a particularly attractive technology for indoor localization because it is immune to interference from other signals, and this is due to its ultra-wide radio spectrum. While its signal, especially the low frequencies included in the broad range of the ultra-wideband spectrum, can penetrate through walls. So you can have the transmitter and the receiver at different rooms. Moreover, the very short duration of ultra-wideband pulses make them less sensitive to multipath effects. And this is the most important features of ultra-wideband because it allows the identification of the main path in the presence of multipath signals. It can provide very accurate estimation of time of flight, which it has been shown in many studies that it can get up to 10 centimeters. Latest smartphones such as iPhone 11 Pro and Galaxy 20 Ultra come with ultra-wideband technology, which makes ultra-wideband a great candidate technology now for indoor localization. Obviously, there are plenty other technologies because of the limited time. We cannot go through all of them, which is the radio frequency identification device or RFID, the Zigbee, visible light, acoustic signal, ultrasound, electromagnetic signatures, and camera-based solutions. So let me go now to the Internet of Things. I will start by giving a prime on IoT. So the Internet of Things, or IoT for short, is based on the fundamental idea of connecting different entities of things to provide ubiquitous connectivity and enhanced services. This can be achieved by embedding anything with sensors that can connect to the internet. So IoT, it tends to create new services and new applications and to improve the performance of different systems related to health, marketing, automation, transportation, retail, smart architecture, and many, many others. And this is something that will affect our lives in the future very, very much. So IoT basically can be divided into three components as following. The first part is related to sensing and data collections, where different sensor or embedded systems connected to the IoT network need to perform specific tasks such as sensing temperature, monitoring user heart rate, tracking objects, etc. These sensors are the fundamental pillars of the IoT system. They are usually energy and processing power constrained devices that are not primarily responsible for extensive data processing. The second part is related to data communication, where the data obtained through the sensors need to be communicated to a central entity, such as a server or a cluster head or any intermediate node. This can be achieved through a number of wireless or wired technologies, as we're going to describe in the next slides. And finally, the final part is related to data processing. as IoT would consist of billions of connected devices, the data generated is going to be huge, as we expected. Therefore, it requires expensive processing, such as data aggregation, compression, feature extraction, etc., to provide the user with valuable and related data. This is usually done at the server, or in the cloud, which then makes the data available to the end user. In the following, I will present and briefly discuss a number of emerging radio technologies, mainly designed for IoT communications, which can be potentially used for indoor localization. First of all is Sigfox, which is founded in 2009, is the first low-power wide area network operator dedicated to machine-to-machine communications and IoT. It operates in the unlicensed ISM radio band. It uses a proprietary ultra-narrowband radio technology to offer a very low, ultra-low data rate of about 100 bits per second, and long-range communications that can reach up to 40 kilometers in open space. The ultra-narrowband nature of Firefox, however, makes it susceptible to multipath and fast fading, which together with long distance between base station and the IoT, we say that the coverage can be up to 40 kilometers, and also the interference in the ISM band can make it Sigfox very inefficient for indoor localization. Next technique is LoRa. LoRa is actually LoRa1 is the medium access control protocol, which is built on top of the LoRa physical layer. LoRa is a proprietary radio modulation scheme based on chirp spread spectrum technology. The uniqueness of LoRa compared to other IoT technologies is the use of CSS modulation, which is a spread spectrum technique where the signal is modulated by frequently varying sinusoidal pulses, known as chirp rate. And these are known to provide resilience against interference, multipath, and Doppler effects. And these attributes make the CSS an ideal technology for geolocation, particularly for devices moving at high speeds. And in fact, CSS was one of the proposed physical layers for the IEEE 802.15.4 standard. However, the bandwidth considered there was 80 megahertz, which is much wider than the typical 125 to 500 kilohertz LoRaWAN bandwidth values. Next protocol is the IET 2.11AH from Wi-Fi Alliance, which is also known as Wi-Fi Hello. Is an IEEE standard specification primarily designed for IoT devices, the extended range application. It is based on MIMO OFDM physical layer. It can operate in multiple transmission modes in the sub-gigahertz ISM bands, using 1 to 16 megahertz channel bandwidths. It can operate in multiple transmission modes, from low rate, able to provide whole house coverage, to battery-operated IoT devices, such as temperature and moisture sensors. And also high-rate modes, able to support plug-in devices with power amplifiers, such as video security cameras. In short-range network architectures, together with the significantly lower propagation loss through free space and walls due to its lower operation frequency compared to LoRa and Sigfox, makes it a good candidate IoT technology for indoor localization. Moreover, in contrast with other IoT technologies, Wi-Fi Hello does not require proprietary hardware and service subscriptions, since off-the-shelf routers are only needed. I think I'm running a little bit out of time, so I will skip the next protocol, which is the wireless, and I will go through some of the IoT and indoor localization challenges. So the first challenge is privacy, and user location privacy is the main concern related to the uses of mobile devices and smartphones. Now, User location combined with the location of IoT devices can reveal far more personal information, for example, related to your health, mood, behavior, and habits. Also, in industrial environments, device locations and movements may reveal potentially confidential information related to the processes and techniques used by a company to develop a specific product. So this is a known open problems, and appropriate methodologies for data collection, processing, encryption, and storage to preserve and guarantee the user privacy and anonymity are needed. And we can use possible solutions, change the MAC addresses or the ID of the devices, etc., to provide more privacy while we can ensure that we can have localization services. The other thing is safety and security, where compromised location information can be very critical for particular IoT application and services, such as structural monitoring, where small changes in the distance between two sensors can indicate a severe stability issues of a building. If someone hacks and changes that information, can affect a lot the stability of the building. Movements of heavy machinery may depend on precise calculations of its distance from several IoT sensors, etc. But localization can be used for security as well. So we can use to locate placed and forgotten devices, where a change of IoT device location may indicate that the device has been compromised, for example, stolen. In that case, we can interrupt the use of the device and delete all the data remotely. Also, authentication of new IoT devices when they come into close proximity to each other can be done through localization. And we can have also create location-based trusted services. What we have then is the heterogeneity and diversity, which is very challenging, because the IoT ecosystem comprises of a large number of heterogeneous and divergent, constantly evolving assets and devices. Up to date, the vast majority of existing localization systems are dealing with a single air interface. So developing ubiquitous localization solutions that simultaneously work with a wide variety of wireless protocols is particularly challenging. Possible solutions is to modify and enhance the firmware or software of such devices to assist localization, or attach supplementary localization sensors of them. However, as you can see in many IoT ecosystems, the device and the networks may belong to different service providers, different users, or different organizations. And we may not have access to modify the firmware or physically attach sensors on them. Another thing is the hardware constraints. So most of the IoT devices are low cost and purpose-made for a particular application. So they have limited computational power. So we cannot run advanced signal processing algorithms. It cannot be used for localization on the IoT device side. They have small size, which make them infeasible to use of multiple antenna or antenna arrays. And finally, is the energy efficiency. Most of them, they based on they have to last for many years based on small batteries. Using localization techniques on top of them can significantly drain the battery. Finally, is the network management and scalability. So interference management is one of the main challenges in IoT networks, and localization techniques can create additional packet transmissions, which can degrade the performance of existing systems, particularly when we operate in ISM bands where everybody is using the same frequencies. And this can be particularly critical in hospital environments where the localization packets may interfere and disrupt other operations of medical equipment. And vice versa, the existing communication network, and particularly again the ISM band, may affect the localization process by causing packet collision or wrong measurements. And since I'm quite over time, 5 minutes, I will try to close this talk with one of the state-of-the-art localization systems. We describe all these techniques, and obviously the accuracy, you will find techniques and companies or research papers, research groups that provide different localization techniques, combining different kind of methodologies and technologies. I want to show you here a company that, a startup that I have the privilege to operate as a scientific advisor, which is solely software-based. It provides interlocalization without using any receivers, only transmitters. So no cables are needed for bulky and expensive device installation. We do not rely on existing wireless networks. They are based on tiny, inexpensive, off-the-shelf sensors, the user-friendly mobile app, and mainly on advanced signal processing and AI algorithms that are running on secure servers. So it goes like this, simple as this. They have a proprietary sensor deployment software that calculates the optimum location of the building walls, where tiny peel and stick battery powered sensor devices, you can see them, the right hand side is the size as a pound, a coin, powered by sensor will be placed, and similar sensors are attached to any assets to be located. The sensor information is located and displayed over the building's floor plan through the mobile app, allowing users to accurately find and locate known location or on their assets. As I said, there are no receivers. All the process is done by the mobile app and the servers. This is the website, whoever is interested for more information there. And here I will conclude my discussions. Thank you very much for attending that. We can answer any questions here. For further questions, feel free to contact me to any of the following emails. Thank you.
Thank you, Thanos. That's a very, very interesting presentation. You've covered an awful lot in breadth and depth, and I'm sure there'll be some questions. So I'd like to hand over now to my colleague, George, who will manage the Q&A for you. Over to you, George.
Right. First question, Thanos, can you hear me?
Yeah.
From John Madison. How much is the localization accuracy affected by the presence of other people, assuming you're trying to locate people in your environment?
It depends quite a lot. I mean, it can go up to a few meters. There are multiple reasons. One is the multipaths, the reflection of the signal on different people, is the absorption of the sensor. I assume that you want to locate a mobile phone. Okay, the absorption of the signal from the body. It also is the directionality of the antenna. So whatever technique you are going to use, probably time of arrival would be, or any related technique to time of arrival would be the most suitable technique for this kind of application.
Okay, thank you, Thanos. Question from Dara Jenner. Are you aware of any indoor localization techniques that are not dependent on radio signals? And what, if any, are the advantages of these over radio signal-based techniques?
Yes, there are things that are based on acoustics, ultrasounds, or other techniques that are based on cameras. Cameras can give you great accuracy, but with the cost of processing, the blind spots that you may have. This is the main advantage of radio signals, that although your signal is distorted, you may avoid blind spots. Ultrasounds you cannot go beyond a room. So you need to have receivers in every room and transmitters in every room, because the ultrasound cannot penetrate through walls. These are the main techniques. Also, there are techniques that they are based on the electromagnetic signature of the environment. Is not radio signals, but every environment has their own electromagnetic signature. It's very similar to fingerprinting technique, but you are just move around with a special device that you record the signature of the particular location.
Can I ask a supplementary to that one?
Yes,
I
yes.
know that iPhone 12 has LiDAR device. And there's speculation about use for that in augmented reality, but localization is part of that, I guess, as well. Can you speculate as to what that can be used for and where its USP might be?
You mean ultra wideband?
No, LiDAR.
To be honest, I'm not really following the iPhone technology that much. But if the question is about augmented reality, this is a great, really add-on service on top of localization, where you can actually put the information that you want to project exactly in the right location in the screen. And this probably what you are looking more there is localization related to the camera and image processing, which is more related to the previous question.
Okay, thank you, Thanos. John McLean asks, what is the range estimation accuracy from both Wi-Fi and Bluetooth?
Again, it depends on the distance between the transmitter and the receiver. Wi-Fi, it tends to, usually in that kind of system, you need to, your Wi-Fi coverage, your network, is usually you have a Wi-Fi router, a server every few tenths of meters. So it is bounded by this kind of accuracy. You will have worse signal. Less accuracy. While in Bluetooth, you are getting a smaller network, smaller rates, although BLE can go in a higher distance. Normally, it will not work that well in more than 20 meters line of sight. So you can get accuracy in both cases up to less than a meter. But again, is how often, what is the outage of this estimation? I mean, you can have that, your environment is changing, you start having some multipaths, everything will go off by half a meter, 1 meter, or few meters. But in general, Bluetooth will give you better localization accuracy than Wi-Fi. It is not because of the radio frequency. They both operate in the same frequency. They're quite similar technologies, although they use different modulation schemes. But it is based on the network topology, the underlying network.
Okay, thank you, Thanos. Two questions of which I think are related. One from an anonymous attendee and one from John. And one question is, iBeacons and Eddystone, are these the techniques used for COVID tracking apps? And do you have any comments on the various COVID-19 track and trace applications and their approach to localization?
Yes. I think, yeah, these are the techniques I think they have been used, although there were issues with that, so I'm not sure at the end if they managed to tackle these issues. So I guess, okay, from the phone, no. From the mobile phone is not the it's not the iBeacon, it's the BLE, it's the actual Bluetooth. I take it back what I said. It's the Bluetooth BLE transmission. It's not Eddystone, or they use the same Bluetooth that is used for communications. And now, regarding the use of these techniques, obviously, in order to achieve that, you need a high penetration in the market, in the population. Lots of people need to use them. If many people will not use them, you will not have the results you expect. The technology works very well. It's a proximity-based solution, which is the simplest. As I described at the beginning, I said there are three types. Proximity detection is the simplest of the three of them. So you will be detected most probably if you have been in close contact with someone else. The point is if that someone else is using the same device as you are doing.
Okay, thank you, Thanos. From Philip Brown, do your techniques draw upon distance calculation systems found in IFF and SSR?
I'm not sure. Can you repeat the question?
Do your techniques draw upon distance calculation systems found in IFF and SSR?
What is IFF?
Philip hasn't explained. Maybe Philip can ask a supplementary and we can get there. I'll
Okay.
move on to the next question for now. One from Prof. Isan Lamy. Do you have some tabular form which shows comparison of the accuracy between the various solutions? And would that be something that they could request from you?
Yes, I mean, we published one paper in surveys and IEEE surveys and tutorial back in last year, 2019. It's a very popular paper. It has received almost 500 citations. And this, we describe all this kind of techniques. So we have tables there. And if you can email me, I can provide that paper, but it's also in archive, so it is publicly available. So there we can have comparison of many different techniques.
From A. Ndolo, how is the sensitivity of the receivers affected by EMI, electromagnetic interference?
A lot. And you have interference either from particularly in the ISM band, which is the 2.4 gigahertz that most of the device, Bluetooth and the Wi-Fi operate. Even a microwave can give significant interference. But the main problem is the receivers themselves. They're not very accurate. Most of the sensors you will find in the market off the shelf, they don't provide very accurate measurements. So you will have jumps in the measurements that you have up to like even like 10 dBs suddenly, some spikes that you cannot really explain why you have that. That's why you need quite a lot of filtering of your signal.
A question from Richard Strike, Thanos. One of the benefits stated for private 5G is localization. Will this use similar mechanisms, and is the performance any different from Wi-Fi, Bluetooth, etc.?
Okay, in general, you have to think. The most important thing, as I said before, is the network. Where exactly are the access points, transmitters or receivers? It depends on what exactly type of localization technique you try to do, are located. Okay, if they're very far away, as we saw in all these IoT new standards, their objective is to have a coverage of multiple devices in a very wide range. So you can go up to kilometers. You want an access point that covers like a few kilometers of range, so big cells. If you are very far away from the access point, what you will have is a huge error, especially when you go indoors. most probably the localization you will get is probably the next flat or the next house. Now what you have, one of the Wi-Fi, the IET, you said the 5G.
5G private, which
5G
may be
private, yeah.
which may be on a factory location or
yeah,
with a particular access point.
It depends again where if they have a technology, a network technology similar to the phantom cell, where you have something, a router installed inside your house, yes, you will have quite good accuracy, comparable more or less to Wi-Fi Bluetooth. But this is quite a proprietary hardware at the protocol. So in many cases, you will not be allowed to play with that. So your operator, mobile operators, probably can provide accurate services. In many cases, other companies may not be able to.
Okay, thank you,
Yeah.
Thanos. Questions about Picolock, I guess,
Yeah.
and one from John Madison and one from Alex Wood. John Madison asks, looking at the website, there's not much info there yet. Does it use Bluetooth in the stick-on sensors, and are they available to purchase for a proof of concept? A supplementary from Alex Wood is, how does your software-based solution work without any receivers?
Okay. It can work with, we use, now they are using so far is Bluetooth technology. So BLE, sensors that you buy off the shelf. You can use any kind of sensor that you buy off the shelf. We just use some tiny ones. What was the question? The second part of the first question?
Are they available for proof of concept?
Actually, we are currently in the proof of concept. The guys there, they are working actually. They are actually doing now the proof of concept. They went, I think, they were quite behind the schedule because of the COVID, because you cannot really have access to public buildings in order to try it. But you can contact the guys, they can provide more information on that, or you can send me an email as well. I can, whenever we have more available information, we can share it with you. Regarding the second question, I mean, this is part of the intelligence. This is something that we cannot disclose at the moment. There is I think the guys have filed a patent on that. So this is something that is pending. And hopefully after that, they will be able to publish that information, how exactly we will do it without using any dedicated receivers. Okay.
I think we need to return to the final question. Unfortunately, we've got quite a number outstanding, but Philip Brown asks, do your techniques draw upon distance calculation systems found in IFF and SSR? And he has noted that the acronyms are IFF is identification, friend or foe, and SSR is secondary surveillance radar. So,
I'm not really familiar with that, so probably I will not give any valuable answer to his question.
Okay, Kevin, I think we've more or less run out of time. It's
okay.
10:08.
Okay, many thanks, George, and thank you, Thanos, for a very thought-provoking presentation. And you've covered, as I said before, an awful lot of breadth and depth in your presentation. And I know from my own work, when I started to look at the near field in RF emissions from telephone wires, then the near field can be extremely complex. So I think it's a hugely complex area, the IoT localization, or indoor localization in the IoT era. And thank you for showing us the theory behind it and the work that you've been doing. Very much appreciated.
Thank
So
you for
Thanos,
giving me the opportunity as well. And if there are any further questions, as I said, please, whoever wants, they can contact me by email.
sure. Yeah, absolutely. So Thanos's email is displayed at the moment, and you know, it's been a great presentation. So thank you very much, and my thanks to George for grouping the questions, asking those on behalf of the audience. I would also like to remind everyone that the webinar is being recorded, and that will be made available on our IET community's website just as soon as possible. And if you look at the bottom of the slide I'm showing, there's a link to our community's website. So finally, I'd like to draw your attention to our next webinar, which will be entitled Agile, just another buzzword, on the 10th of December. And the one after that is entitled Nobody Saw It Coming, The Rise and Rise of the Camera Phone. And that's on the 26th of January, 2021. The committee is working on putting together other webinars for 21. So please keep an eye on our community's website for details, and check that for further details of webinars and how to register. So finally, on behalf of the IET Anglian Coastal Local Network, thank you all for joining tonight, and thank you to the team who put tonight's webinar together. And also thank you once again, Thanos, for the work that you've done in putting the presentation together and delivering it tonight. It's very much appreciated. So that concludes the webinar now, and you may disconnect. Thank you.